right, it's time. Let's get started. So earlier in the last lecture, we discussed the properties of a sequence of IID Bernoulli random variables. Right? And we discussed the convergence of the sample average Vn to the true average, to true mean value mu, and we saw that we can show that kind of convergence using either the Chebyshev rule or the Hoeffding rule. Sorry about that. Let's try again. Ah, okay. Some of the no. Ah, okay. Yeah. So we have those bounds, and of course we say, well, why do we want to study a sequence of IID Bernoulli random variables? Well, because our error measure, right, the per sample error is an indicator function, which is a Bernoulli random variable, right? So, and therefore our E in of any hypothesis H is a sample average of this indicator function, which is Bernoulli random variables. Yeah? And then our E out, our test error is a statistical average or the true mean value, so it's expected value of this error. Oh, sorry, this is this n, yn and xn here for the n sample. Right? But for the E out, we don't have n. Yeah, we can only say, given any particular sample x, what is the expected value of that indicator function? Of course, this is, we also know it's a probability that y is not equal to h of x. Yeah? Right. So therefore, we can convert this to the general probability problem, the general sequence of Bernoulli random variables. Right? So I'm just pretty much repeating what we have already alluded to when we discuss the Bernoulli random variable. Yeah? So, but there's a small caution here. Okay? So for any hypothesis, we can do this. For any given hypothesis, H, of course that's in the hypothesis set H. Yeah? If this hypothesis is selected before we see the data point, okay, that's very important. Before we observe the data. Okay. So in other words, H is independent of the data, right? Okay. Then we can, let's say, if we define this Z as the Bernoulli random variable, y is not equal to h of x. Yeah, of course, Zn would be 1, Yn is not equal to Hn, right? This is specifically the nth training sample that we have. Okay. Then, if this is the case, then we have an independent sequence of Bernoulli random variables. Why is that? Because the x, these data points, they were chosen independently. Okay? So because x1, x2, all the way to xn, they are chosen IID from the distribution P of x, right? That is our setup to begin with, yeah, for pack learning. Since each one of these random variables, they are independent, each one of these guys is independent, this whole function across different n values will have to be independent as well, right? Knowing one will not tell you anything about anything else. Yeah? Knowing whether one point is in error will not tell you whether the other point is in error or not, right? They are all independent. Yeah? So therefore, our Zn are also independent. They are indeed independent Bernoulli random variables. And this is important because now, because they're independent, then we can use the analysis that we did last time, right? They are IID Bernoulli. So now we're going to we can define this H in Zn. Yeah? It's the sample. Of course, this is we call it Vn before, right? And the E out, the test error, is again the expected value of Z. Of course, we called it mu before. Yeah? And because of the independence sequence, all of the conclusions that we have from last time, they hold. Yeah? In particular, from the Hofding inequality. Yeah? Oh, come on. Inequality. Yeah? Tells us that the probability that this random variable, that the sample mean, is a certain distance away from the true mean, which is E out, right? The mu, yeah, greater than epsilon. Right? Well, let me just write this, yeah, in case you forgot. This is our Vn minus mu, greater than epsilon, right? That's the form that we saw last time. Yeah? And this is upper bounded by 2 times E minus 2n epsilon square. Yeah, right? This is true for any epsilon that you want, right? Any positive epsilon. You can make epsilon as small as you want, and this bound still holds, right? That's what Hofding inequality tells us. And in fact, we're going to define this as delta, right? We call this delta. So that 1 minus delta becomes our confidence level. Yeah, that's the term that we used last time. Right? So this tells us that for any delta that you want, or that any general positive delta, we can guarantee that with a probability that's greater than or equal to 1 minus delta. Yeah? So this is our confidence level. Yeah? We're confident that this distance minus E out. So this is a generalization error. Yeah? Is less than or equal to epsilon, of course, and which is equal to 1 over 2n log of 2 over delta. Right? That's the same form that we have from last time. Yeah, right. So our test error will be very close, can be very close to the training error. Yeah, as close as you want, epsilon. Yeah, depending on what confidence you want and how many data points you have. Right. Okay. You can always choose n and delta to make epsilon small enough. Now, another thing to know is that usually we don't care about, this is a magnitude, right? So there are 2 sides. This you break out the magnitude. One side is positive, the other side is greater than or equal to something negative, right? Usually that side we don't care about. So we're going to only look at the side where E out is upper bounded by something. Right? We don't care about the lower bound to E out in general, unless you do some really important research work For now, we just care about, let's say, just the upper bound, how bad it can be. Then we just write this side, one side of it, so that we don't have to work with a magnitude, absolute value. Okay? Yes? Yes, yeah. All logs without specifying would be the natural log. That's the convention in most books. So that's the upper bound to the test error that you can have, right? So therefore, that tells you that, well, the test error cannot be too much higher than the training error. Yeah. If you have a way to minimize your training error to make the training error small, then you can actually make your test error small as well. Okay? With a certain probability, yeah, you can guarantee that your test error can be small as well. And in fact, this thing approaches E in, right, as n goes to infinity. Yeah? If you have infinitely many samples, then your training, and if you can minimize E in, then your training will be very, very good. Yeah? Your training will be very good, and also your, when you apply this model, this trained model to the real world, it will also perform very, very well. Yeah? Because your test error is the same as a training error. So this is pretty much repeating what we have already seen from last time, right? Yeah? So, and that's the conclusion. So this is very nice. So learning is possible, right? You can use the data that you have to train the model, to learn from the data, and then the model can work very well in reality, yeah? Even when you have data points that you have not seen, yeah? And by this analysis. Now, you don't know for sure. Everything is probabilistic, yeah? Because it's a random system, right? But then you can set this delta to be small, so you have very high confidence that your model that you train will work very well during testing. Okay, make sense so far? Yeah, that's what it says. So far, so good, right? But of course, this is too easy on us, yeah? It's not quite so easy. Okay? So here, it's a very important assumption. Remember, we say this is true if you have a hypothesis that is chosen before you observe the data D. Okay? Yeah? But that's not what we do when we pick the hypothesis in training, right? We use the data D to train. And then based on that training, we pick the best hypothesis. Yeah? So clearly our final hypothesis depends on the data, right? Okay? When you have the hypothesis depends on the data, this independence assumption is no longer true. This independence conclusion, no assumption, is no longer true. Yeah? Because the z's for different n values, they are no longer independent of each other. Because each one of them depends on the entire data set, right? Yeah? If you use the G that you pick. Okay? So that's the trouble. Let me write it down, and then meanwhile, let's think about it a little bit more. So the trouble is that our analysis above is for IID Zn sequence. But our final hypothesis does not give you that. G is selected after, after observing D. And clearly you have to do that, right? Otherwise, your training error will not be small. Yeah? To make your training error small, you have to observe the data points and then find the best hypothesis to minimize the training error, to keep E in G small. Okay, so there's a conflict there. And therefore, we know that this G of x1 all the way to G of xn, these functions, they are no longer independent. Yeah? They all depend on all of the data points. Yeah? Even the individual data points, they're independent this sequence are not an independent sequence anymore. Yeah? Are not independent. Okay? So we cannot use this Hoeffding bound anymore. In particular, yeah, the Hoeffding bound does not hold. Hoeffding inequality, does not apply. Okay, everyone okay with this point? Why this we have trouble when the hypothesis is actually our final hypothesis after training? Right? If you just look at these guys, looks like they're independent, right? Because each one of these data points is independent. But then our G itself depends on all of the data points. Yeah? So that's the issue, right? If you just say arbitrary pick a hypothesis, then they indeed this will be independent, right? If H1 of x1 and H1 of xn will be independent, right? It's just given any particular hypothesis, you have an independent sequence. But not when you have this specifically optimal hypothesis. So that's a big problem. Yeah? And we have to find a way to deal with this. Okay? So, well, we can, to some extent, solve this problem by using the union bound. Okay? I hope the term rings a bell to most of you from EC302 to the union bound. For example, if you have two events, what is the union bound? We have A and B like this. It's a Venn diagram, right? I hope all of this looks familiar to everyone, I hope. Yeah? So what does the union bound say on this diagram? The union of what? Well, only two things there, right? The union of A and B, of course. Yeah? The union of these two events. What does the union bound say? No? Nobody? That's not ring a bell at all? EC302, one of the first things that you will learn in EC302, yeah? It's all of A and B, the union of those two events. It's the same as A or B, right? We want to find the probability A or B. So either the probability of the event, either A or B occurs, yeah? A union B is equal to the probability of what? Oh, no, it's a bound. Upper bounded by? Yeah, that's right, the sum of their probabilities. And it's really easy to see from this picture, right? You can view this as two objects, and the probability would be their mass. But these two objects overlap, yeah? When you look for the union of these two, it's just this thing, right? Because of overlapping, if you just add up the probability, you're double counting the intersection part. Yeah, you're counting this twice, right? So clearly, the right-hand side will be bigger. Yeah, so that's the union bound with two events. We can generalize this to m events. So in general, we have for any set of events, A1 to AM. The probabilities of their union is upper bounded by the sum of their probabilities. So I goes from 1 to m, AI, less than equal to the sum from 1 to m, the probability of AI. Okay? That's the famous union bound. It's one of the most fundamental theorems in probability. And we can say one more thing. When is this inequality exact? So it's equal. When do we have equality? Well, turns out it's an if and only condition. If and only if. Yeah. When are they exact? Yeah. Yeah, they are mutually exclusive, or in other words, they don't overlap at all. Yeah. Clear. It should be very clear from the example of when you have two events. If they don't overlap, then yeah, there's no double counting, so they are exactly equal. So if and only if A1 to AM, they are mutually exclusive. Yeah. It's just a fancier way of saying that they are disjoint. Yeah, they do not overlap. Okay. So how do we use the union bound to handle our issue of looking for this generalization error for the final hypothesis G? Okay. So there's an interesting trick here to say that, well, the G is chosen from the hypothesis set, right? G is one of H1, H2 to all the way to HM. Yeah, G is one of them. So if you want this bound to be true for G, then this, as long as I satisfy the bound is true for any hypothesis, then it's okay. Yeah, and that would be in a way it's one of them. We just need one of them, one of these hypotheses to satisfy that bound. Yeah. So that's how we get a union. So since G is in H, in other words, G is one of, we don't know which one, but we know there's one of them. Yeah, this M hypothesis. Yeah. Now the event that we want, which is E in of G minus E out of G greater than epsilon, this event is going to be as, well, let's compare with this event that are union everything together for all HIs. E in HI minus E out HI is greater than, or I need to put a curly bracket just in case indicate this is the event. Yeah. Okay. If I union all of these events over all hypotheses, what is the relationship between these two? Is there any relationship at all? Can you say something about which one is bigger? Yes? Yeah, well, yeah, no, I'm just saying that these two first. Yeah, yeah, I know we use union bound on this one, right? That's what we're going to do. Yeah, but right now we have to decide these two. What is the relationship between these two? Yes. Greater than or equal to? Are you sure? This one is greater than or equal to that? Remember, this G is only one of them, right? This G is one of these guys inside the union. Yeah, certainly this one should include that one, right? Yeah, this one is one of them. We don't know which one yet, yeah, but it's one of them only. So it has to be a subset. Okay, so subset. Yeah, Aaron, okay, okay, yeah. So therefore, the probability will be less, right? The probability of subset is always less than the probability of the bigger set. Yeah. So hence, we have the probability of so much writing, but just pretty long writing, but the idea is very simple. Greater than epsilon. Oh, I just took curly bracket. It's less than or equal to the probability of the union. I equal to 1 to M. EI. Not EI. Oh, do I have EI? E in, sorry. E in. Yeah. E in HI minus E out HI. This distance is greater than epsilon. Yeah? Yeah? Because it's a subset, right? The probability has to be less than or equal to that. And now we can apply the union bound. Yeah, so this is less than or equal to the sum of the probabilities. 1 to M, the probability of this E in HI minus E out HI greater than epsilon. Right? Now, by this stage, what more can we do? What is the next step once we have this? Now can we use the Hoeffding bound? Is the Hoeffding bound applicable now for this error? It is, right? Because this is for any general HI, right? This is any general HI. It has nothing to do with the data set. Yeah? Each one of them satisfy their independence. So we can use the Hoeffding bound. Yes? G is the final hypothesis after training. So you look at your data, you pick the best one, that's your G, right? HI, they're just all of the hypotheses in your hypothesis set. Yeah? So this one has nothing to do with the data at all. Yeah? They are there whether you have the data or not. Yeah? So therefore, this one now we can apply it Hoeffding bound. So this is less than or equal to 2 times E minus 2 epsilon squared. Yeah, this is because of Hoeffding. Okay. Well, of course, we have to sum up all of them. Therefore, we have to, at the end, it's just multiply by m. Right? So this is 2 times m E minus 2m epsilon squared. Okay. So what we get at the end, we still have upper bound on this error for G, yeah, to find the hypothesis. Except that now this solution, if you compare with the previous one, we have to amplify it by m times, where m is the number of hypotheses you have in the hypothesis set. Yeah? Is this a tighter bound or a weaker bound? It's a weaker bound, right? It's a wider, yeah? So our guarantee is less now, yeah? Okay? For the final hypothesis, we can guarantee less than for any particular hypothesis, yeah? It's a very interesting notion there, yeah? So note one is that when G it's in H, of course. In H, it has M hypotheses. So HM is selected after observing the Hoeffding bound. In fact, if you use the Chebyshev bound, same thing, yeah? It's going to be weakened by a factor of D, or of M, sorry, yeah? But to some extent, it's still okay. If I, again, let this delta equal to this 2m, e to n epsilon, let's see what happens, yeah? Then that means my epsilon will be square root of 1 over 2n log of 2 times m over delta instead of simply 2 over delta. Yeah? Okay? So if my n is large enough, I can still cancel out the impact of m. Right? So we're going to define this so-called generalization error. Let me see. Let me just define it here. The so-called generalization error. Which is delta G is again, just the distance between this two, yeah, E and E out. So then from this equation above, on top, then we can say that with probability 1 minus delta greater than or equal to 1 minus delta, we can guarantee that this generalization error to be upper bounded by 1 over 2n log of 2m divided by delta, right? And if you want to say, well, I only care about one side of the error, so that means E out of G is less than or equal to E in of G plus this thing, right? If you don't care about the magnitude. Yeah, so this is guaranteed with probably 1 minus delta. Yeah, of course, if your 1 minus delta is very large, close to 100%, then this delta will be very small, and this thing could be large. Yeah, it's a trade-off. Yeah, probably approximately correct. You can have just one of them. You have to talk about both of them. Yeah, what is the probability, and what is the approximation error? Right? Okay. So very nice. With the union bound, we can still say something about our final hypothesis, even though we no longer have the independence. Okay? So let's look at this and check what's the difference between delta G and E in. Yeah, well, there's a trade-off, it seems, right? There are two terms, right? The test error depends on two terms. How good you can train to get to pick a good hypothesis for training, and then once you pick that, how far away is the E out to your E in? Yeah. Okay. So let's look at these two. There seems to be a trade-off between those two. Yeah, those two terms. So we can have delta G on one side, and then we have E in on the other. Like that. And let's study. Well, let's have one more column. Impact of N and M on these two. Suppose let's look at N. Suppose we have a larger and larger data set. Yeah. Big data, very big N, what happens? Delta G, of course, will be, if we increase N, then delta G, the generalization error goes down, right? Yeah. The more training data points you have, turns out that your training error and test error become closer, so decrease. Yeah, not decrease. Yeah. How about E in, though? If I have more and more data in my training set, you might expect, well, it gets harder and harder to optimize your hypothesis given the data set, right? Suppose you have a fixed amount of computation power. Yeah? You have the same computer, fixed amount of memory, fixed amount of time that you can run your computer to find the optimal hypothesis. You expect this optimization becomes harder and harder as you have more and more data points. Think about the PLA, the perceptual learning algorithm, right? You have to look through so many data points, right? Yeah? Harder and harder to find optimal solution. So in general, this one actually increases. The in-sample error increases. Okay? So because this is more complexity in optimization, or more complex optimization. Okay, of course you say that, well, if I can scale up my computational complexity over N, that's a different story, right? So here we are saying keeping everything else fixed. Yeah, fixed computation capability, fixed time that you have to do calculation, then your E in will increase if you have more training data points to handle. So then there's a clear trade-off between those two. Okay. Now how about in terms of M? M is the number of hypotheses we have. How complex my model is, right? The more complex the model, the more hypotheses inside that you can choose from. Yeah. If you have many hypotheses to choose from, how about delta G? Which one is, what happens to delta G? Well, clearly M is on top, yeah? So this increases, right? The generalization error increases. Why do you think is that? Why does the math tell us the generalization error increases as M increases? Do we have a more intuitive explanation for that beyond just looking at the math? Why do you think this is the case? Yes? Exactly, yeah. The more complicated your model is, you fit into your training data better. But then fitting better to the training data usually means that you are fitting worse for the, you're doing worse for the test data. Yeah, you're overfitting. You're fitting to the noise in your training. Yeah? But how about training error? Of course, the training error now is decreasing. Yeah, because you're fitting better to your data points. Yeah, so the EN decreases. So again, there's a trade-off in terms of M. Yes? No, number of hypotheses. Right? We have H1, H2, all the way to HM. Right? Yeah, the number of hypotheses in the hypothesis set. So this one is because there are more choices in the hypothesis set H to choose from. Everyone okay so far? Yeah? So we have this kind of trade-off. So, but let's draw a picture just to make this point a bit more concrete. So if this is the error, and we want to see the total error as a function of n, right? So if we change n and we fix m, yeah, and fix everything else, the computation capability and the time that you have, fix everything else, we just increase the number of data points. And we see, well, of course, the delta G decreases. Yeah, delta G looks like, let's say, like that. The generalization error, right, at the end. But then your training gets more difficult, so your E-in increases. Training error increases. But the test error is roughly a sum of these two, right? It's upper bounded by the sum of these two. So the test error in general looks like there's a dip, right? It initially decreases, but then the E-in part dominates, so you could pick up again, right? So therefore, this one would be your E-out. And E-out is the ultimate measurement of how good your learning is, right? That's when E-out is the only one that matters. Yeah? So, and then you see the dip like that, there's an optimal point somewhere. Yes?
Why would E-out increase if you have more data?
Well, because E-in increases, right? Your training gets worse and worse, become more harder and harder. Remember, the E-out is roughly a sum of E-in plus the generalization error, right? If your E-in, if you cannot optimize well during training, clearly your learning will not be very good. Okay, everyone okay with this point? Yeah? And we can do something similar, pretty much the same thing for in terms of M. Yeah, it's a very interesting thing. So it's not true that the bigger the big data, the bigger the better, right? At some point in time, you have to match your data set that you want, the size of the data set, and the ability you have to optimize it. Yeah? In terms of M, of course, the E-in decreases as M increases. So E-in goes like this. And then delta G, unfortunately, goes up. So there's no free lunch. Yeah? Always one goes up and the other one goes down. And again, you have a E-out that dips down, but then eventually it goes up. It does not stay going down. Anyway, yeah, it's E-out of G like that. Okay, and you can find, well, maybe there's an optimal point here for the model complexity. Yeah, so this M star, optimal model. So if you have to pick a model, do I pick a linear model, quadratic model, or neural network? Yeah, say, well, there is an ideal point. It's not true that the more complex your model, the better. Yeah, that's not true. So the ideal model complexity. Okay, and again, as you imagine, for a linear model, we have a fewer hypotheses than a quadratic model, and we have a fewer hypotheses than a neural network. Yeah, okay. So complexity. So this line you can replace this M by different orders of polynomials or SVM and neural networks and so on. Okay. Yes.
I don't get how H is independent because, like, whenever you train a learning model or like machine learning model,
H is in. You said H is independent.
yeah, like hypothesis, like the hypothesis, okay. Like all of the hypotheses that we're training with, we see in the data, and then we're training.
No. The H1 to Hm, they are there, right? The hypothesis set is there. It's independent of the data itself, right? The data set is. There are two separate things, right? You have a set of hypotheses that you can choose from, and then you're given a data set. So the individual hypotheses are independent of those data, right? It's there no matter what the data is.
Okay, and the different hypotheses be different weight vectors?
That's right, yeah, exactly. The different weight vectors, right? As you imagine, they have nothing to do with the data that you're given.
Okay, but wouldn't that be infinity?
That's a very good point. That's what we're going to get to, yeah? Okay. So far, this is fine if M is finite. This bounds still, it's very helpful. We can get these nice conclusions. But very often, in fact, most of the time, for any realistic machine learning model, our M is infinite, not just linear classifier. It's infinite. How do we deal with that? Okay, that's the second trouble that we have to deal with. That's why we still have 10 minutes before the lecture ends. Yeah? But nevertheless, this will still apply. Okay, this issue of model complexity, as you go from a simpler model to a more complex model, the EL will still go down and go up. Okay, whether this M is infinity or not. Okay, you should know by now the different levels of infinity, right? Some infinities are bigger than the other infinities. Yeah, there's more complexity and so on. So this still applies even for M in infinity. Okay, the only problem is that when M is infinity, our bound up there is a bit meaningless. Yeah, right? Okay, so that's the trouble. Oops, new trouble. For most learning problems, models, M is infinity though. So there's just one example, in case you forget, perceptron learning, perceptrons. It's a linear model. Any choice of W and B is a hypothesis. Any choice of W and B is a hypothesis. And clearly we have infinitely many of them. And in that case, the union bound is no good. It's not tight enough. It's too loose in that case. Okay. So how can we do better? Yeah. But first of all, we have to recognize why union bound is too loose. Yeah. Union bound too loose. Union bound is loose when there's overlapping. Right? Remember, union bound is tight when those events have no overlapping. Yeah? Remember? Yeah. When they don't overlap, then it's tight, right? So let's look into this. So the bound is tight, or bound would be tight, if and only if the events of this form, E in hi minus E out hi, this distance greater than epsilon, are disjoint. Right? Yeah, that's just simple probability. Yeah? If they don't overlap, then you get the sum of the probabilities. But if you look at this example, just in two-dimensional space, x1, x2, I have plus, 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 I don't know, minus, 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 whatever. Yeah. So if you look at, say, an h1 and h2, what do you think? These two hypotheses. Of course, these data points are our given D, right? This set of data points for this particular set of data points. There are many, many hypotheses that looks like this. These two, they're pretty much the same hypotheses, right? With respect to this data point. Yeah? Okay. And you expect that during testing, they're likely also to perform the same. Yeah? If they're good, whether they're good or bad. Let's say good means that the generalization error is less than epsilon. Bad generalization error is greater than epsilon, let's say, right? Okay. They're likely to be the same. Okay, so let me write it down. For the same, for some, well, as you can say, for some given D, it is highly likely that H1 and H2, they are not mutually exclusive. So let's say they are both good or bad. At the same time. Either they're both good or they're both bad. Because maybe they're close to each other. Yeah, good or bad meaning, again, this E out, HI, greater than epsilon. Well, let's say question mark, yeah, greater than or equal to. Okay? Well, less than or greater than. This is bad or good, I guess. Yeah. So it turns out that they not disjoint events. Yeah? Okay. So that's the problem with using a union bound. Yeah? We multiply by m, where m is the number of hypotheses. But then for a lot of the hypotheses, there's a heavy overlapping. Yeah, so therefore the union bound is loose. Okay? And that leads to a kind of an obvious solution then. What if we simply treat H1, H2 as the same hypothesis? Yeah, if they're close enough, then we treat them as the same. We don't count them as a separate hypothesis. Right? So would that help? Yeah? Reduce the value of m. So in other words, we want to find an effective number of hypotheses. Yeah? Some kind of a distinct hypothesis. Yeah? Okay? So, and that's the solution that we will have to go to when we deal with infinity, when m is equal to infinity. Yeah, that's the only way to do it, to substantially reduce their number. Otherwise, you stay in infinity and those bounds are useless. So therefore, we need a concept of effective number of hypotheses in our hypothesis set. Yeah? What is the idea for this effective number? Well, you can see on the picture there already, right? That if the two hypotheses give you the same separation of pluses and minuses, we can just treat them as the same, right? Okay, so therefore the main idea is to say, well, given the data set, D, we say that two hypotheses, let's say H1 and H2, effectively the same. If they give the same labels, even though the parameters W and B are different, right? But if they give the same plus and minuses, have the same label for every data point, of course, yeah? So same label, I guess, i.e. H1 of x is equal to H2 of x, yeah? And this is for every x. X, that's in D. Then we can say that they are the same. Okay? Now, how do we mathematically expand on this, make it precise? Yeah? We're going to take a break, and then we'll come back to discuss that, the mathematical details of this idea.
I asked this question in Piazza, and
Okay, let's restart, okay? So yeah, today's materials will be a bit mathematical. I hope everyone is doing okay after the first half. Yeah, the math is not too bad. Right? It's understandable, I hope. So in order to deal with infinite m, we have to find the effective number of hypotheses. And we say, well, one way to deal with this effectiveness is to say that, yeah, we just observe what kind of pluses and minuses the hypothesis can give us. They give us the same pluses and minuses, then we say that these two are the same hypotheses, right? So therefore, we have to really look at what kind of vectors, the plus and minus vectors, the hypothesis will give us. Yeah? And that's part of our today's analysis since the second half, the so-called VC generalization bound. What VC means will become clear very fast. It's just two people's name. Yeah? Dichotomy is the, I think that's how you spell it, dichotomy. Just plus and minus, yeah, because we're talking about binary. Yeah. So if we, again, we have the data set. D-dimensional space, be some given data points. That we already know. And then, of course, we have a set of hypotheses. There are m of them. Is the hypothesis set. Yeah, of course, each one of them would be a mapping from d-dimensional space to -1 plus 1. Yeah? So now we're really trying to study the effective number of hypotheses. Yeah? Despite totally we have actually m of them. So we're going to have to define what each hypothesis can do, what kind of plus 1 minus 1 each hypothesis can give us, right? So therefore we obtain this so-called dichotomy vector corresponds to the data points that we have for some hypothesis that's in the hypothesis set. Yeah, we define it as simply this: h of x1, h of xn, right? There are n data points. Each one of them, the hypothesis will give you either -1 or 1, right? And of course, this now we have a vector of -1 and 1, so a binary vector. Yeah, if we say binary, we don't, we just use -1 and 1 to represent it, right? Instead of 0 and 1, just for convenience. So this binary raised to the nth power, this is basically a length n vector of -1 and 1s. Yeah. Okay. So therefore, this one basically represents pretty much the characteristic of this hypothesis, right? Later we're going to say, well, if two hypotheses give me the same binary vector, then I can view these two hypotheses as the same, right? So in that case, if we put these vectors together, this dichotomy vector together into a set, but there are m different vectors. So each vector corresponds to one hypothesis. There are m of them. But they are not all distinct, right? Some of them will give you the same vector. Yeah? Different hypotheses can give you the same vector. Right? So when you put them into a set, because a set does not allow repeating elements. Yeah? So the element set will be much smaller than the number of hypotheses. So dichotomy set for h, let's say, well, with respect to the data point that we have, x1, xl. Yeah. We use the notation of h, but with a bracket, x1 to xn, like this, okay? That's the notation for this set. It's simply the set of all of these, I should say, yeah, h This is the dichotomy vector, and then the set of vectors such that the H is inside the hypothesis set. Oh, I'm sorry, I should use a set notation. This is not curly bracket. This should have been curly bracket, yeah. Set notation. Okay. Everyone clear what this dichotomy set is? Yeah, just this set of vectors. That's all, right? Nothing mysterious, even though a lot of writing. Yeah. And the note is that this, there are no repeated elements in the set by definition. There are no repeated entries. In a set, right? I mean, you all know that, right? From elementary school, probably. Yeah. So, therefore, how many possible? This size of this set would not be equal to m, right? It will be less than m, yeah? In general, well, less than or equal to m. But in fact, we can give a better bound if m is infinity. Right? What is a bound to this size? The size of this dichotomy set? Huh? N squared? Your high school teacher will be ashamed of you. 2 to the nth power, the other way around. 2 to the nth power, right? So, no matter how big m is, yeah, you can have infinitely many hypotheses, but they can only be up to 2 to the nth power distinct binary vectors, which is, kind of obvious idea, right? So, no matter how large, this size, yeah, this one is, yeah. Okay. So therefore, one might be saying, well, yeah, then this one, we could use this one as a effective number of hypotheses, right? Yeah, based on our objective to begin with. Yeah. Even though they are different hypotheses, but then they may be doing the same thing anyways. So, but there's a question mark here. Is this the right thing to do? Well, we don't like it because this one depends on the data points, right? Depending on what they are, x1, x2 to xn. Yeah? So, not very convenient to use, not very convenient for our, even if we use this as a bound, in our bound, but then this bound only works for this particular set of data points, right? That's not nice. So we're going to define something that's independent of this number of data points. But before we go there, let's study this a little bit more closely, this number, this size of the dichotomy set. So we're going to write a new definition called shattering that we are not going to use. It's a very, very useful definition for general machine learning analysis, but not very useful for our course. But so I just want to introduce this term, but we don't use it too much. But it's a Q definition. Okay? We'll say the hypothesis set is shattering the points x1 to xn if, in fact, this size here is exactly equal to 2 to the n. So it reaches the maximum, okay, 2 to the n. Hypothesis set n, we'll say that it shatters. The data points x1, xn, if size is exactly 2 to the nth power. In other words, this H is as diverse as possible, right? There are enough hypotheses there to give you all possible binary vectors, right? There are enough hypotheses there to give you all of the binary vectors. Yeah? So i.e. H is as diverse as possible. But with respect to the data point given. Yeah? Everything here is with respect to the data points given. Yeah? So let's look at some examples. So d equals to 2. By the way, the term is so shattering. Basically, you can distinguish these data points as much as you want. Right? Remember, say, the linear case, right? And any kind of plus minuses you can get. So you kind of distinguish the points in all kinds of ways. Yeah? Label them all kinds of ways. So that's the meaning of shattering. So let's suppose we have two-dimensional space, and H is the linear classifiers. So all linear classifiers. So in other words, we have the form of sine of W0 plus W1 x1 plus W2 x2. Like that, yeah? So let's look at this example here. 3 points. x1 is here, x2, x3, like that. Yeah, just 3 arbitrary locations. And we ask what kind of binary vectors can we generate by the linear classifier. So we can have h of x1, h of x2, h of x3, right? You can have plus, 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 right? And then you can have plus, plus, minus, yeah? Plus, minus, plus, just write it down systematically like that, and then the rest will be minus, yeah? And the minus side turns out to be just symmetrical. You just flip the order. So you really, for any conclusion, you just need to study one of them, you know, the plus side, and then the rest will be by symmetry. And we ask for all of these possible dichotomy vectors, basically binary vectors. Yeah, so I don't know why people use dichotomy, right? I would just call it binary vectors, much easier to understand, right? But no, they call it dichotomy vectors. Oh, because it's minus and plus, yeah, I guess. Anyway, the question is there a hypothesis that can give me that vector? Yeah. Is there such H? Edge of the laptop always gives me trouble. Okay. Is there such H that can give me that binary or dichotomy vector? So the first one, plus, 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 what do you think? Is it easy? How do I get plus, plus, plus? Which hypothesis? Come on. This is the easiest thing to do, man. Yes? All ones? Yeah, they're all ones, of course. By definition, they're all ones. But where is the line? Yeah, we want to. A hypothesis is the line, right? The line to give you this plus, plus, plus. Yeah. Okay, that's too specific. You don't have to be so careful. Let me just say, I can draw a line here, right? And say, well, all of this side is plus. The other side is minus. This hypothesis will give me plus, 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 right? So, obviously, right? Yeah? Everyone okay with this? There's some, some doubts there. This is a hypothesis, right? The blue line is a hypothesis, and this hypothesis will give us plus, plus, plus. So we're all set, right? We just say that there is such a hypothesis. And we can draw it. I can show you this line. Yeah? So yes, this one can be done. Right? Everyone okay? Yeah? How about the second one? The second line. the second vector, let's say, yeah, plus, plus, minus. Can we generate it? Yeah, yeah, I can, let's say, plus, plus, right? I can have this side, right? Si plus. Yeah? So there exists a hypothesis for me to generate this vector. Of course, there are many, many other hypotheses that can generate the same vector. And that's the whole point, right? Those are all equivalent hypotheses anyways. Yeah, that's the whole point. So, but anyway, right now we're just asking whether there is such a thing. Yeah, there is. Okay. And how about the third one? Well, of course, you can easily check. Yeah, you can do it. Yeah, all four of them, you can do it. And then for the rest, as I said, this is by symmetry. Whatever that you can achieve for the plus, you can also achieve for the minus. Just flip the line, flip the arrow, right? So this, the four of them would be okay. Yeah. So therefore, in this case, the total number of distinct dichotomy vectors that we can generate is 8. Yeah. And of course, it's 2 to the third power, and where n is 3, right? So therefore, this is called shattering. Yeah. In this case, the linear classifiers can shatter these 3 data points. Now, so far so good. Any concerns? Yes. Shattering is simply that the total number of distinct vectors that you can generate is as high as possible. And 2 to the nth power is the highest possible. So now I can, right? I can generate all 8 of them. Yeah? Yes.
So like we would say it doesn't shatter if there's like some sort of combination of ones and zeros we can't.
That's right. Yeah, yeah. If there's some combination we cannot generate, then we don't shatter. Yeah. Can someone think about a case where you cannot shatter? Yeah.
Well, it's like what we had like on the midterm where it's like 2 ones and 2 zeros there.
Yeah, that's for 4 points. We'll get there. We'll get there. But for 3 points, is it still possible to have? Yeah. Yeah, they're all on a line. Okay. So it turns out the location of those points matters. Yeah, it matters whether you can shatter or not. Okay, whether you can have as diverse a outcome or not. Okay, so the first thing to note is that the location matters. Yeah, if you look at this, oops. X1 here, X2 here, X3 there, it's on a line. Yeah. Then we ask, well, let's say correspond to above, we have plus, 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 minus, plus, minus, plus, plus, minus, minus, and da, da, da. Yeah. Clearly, plus, plus, plus is easy, right? Just put a line somewhere in the corner. Plus, plus, minus is okay, yeah? Plus, plus, minus, I should put a line here, right? Put a line there, you can do it. So that's not the problem. The third one is the problem, right? Plus, minus, plus. There's no way you can use a line to generate that, yeah? So this one turns out to be no good. We cannot generate this one. The rest you can generate, yeah? Oops. In fact, again, by symmetry, you know that there's another one down there for the negative one as well. There's another minus there. Yeah. So you don't have to check that very carefully. Just symmetry is enough. Therefore, in this case, for this particular 3 points, that's why this is always a function of the data point, the set that we're given. This is equal to 6, less than 2 to the 3. Yeah. So not shattering. That's this. So that's why we don't quite like to use this one directly, yeah, because it's highly dependent upon the location of the values of those xi's that you're given. Another observation we're going to make is that for a larger n, when we have more number of points, do you think it's going to be easier to shatter or harder to shatter? Why? Why harder? Yes? Yeah, so therefore it's harder to shatter, harder to separate all of them. Yeah, that's right. Because you have more points and, just purely there's more cases to handle. So harder to shatter. Okay. So let's look at the case of 4. Let's say, I don't know, 1, 2, 3, 4, like that. Doesn't matter how you name them, x1, x2, x3, well, it's 4, x3, like that. Yeah. If you want to do I want 1, 3, yeah. I think this is 4. Yeah. Of course, there are now 16 possibilities, right? Plus, 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 minus, plus, plus, minus, minus. Oh, well, I'm not going to write down all of them, right? Because there are too many. I'll get to the one that gives you trouble. As you already know from the midterm, and well, we've been using this example forever, right? Plus, minus, and then minus, plus, minus, plus, yeah, and then minus, 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 yeah. Okay. So plus, plus, plus is, again, this one is easy, yeah, and then plus, 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 minus, also easy, just the corner, right? Set the line that cuts the corner. It's the problem with this one, right? This one, plus, minus, plus, plus, minus, plus, minus, yeah? So the classical non-linearly separable case, yeah? It's non-linearly separable, so we cannot have a linear line to get that plus or minus, right? So really, this is no, okay? And of course, the corresponding one, minus, plus, minus, plus, also no, yeah? The rest is okay. The rest is all okay. So this is the only two that we cannot make. Okay, you can easily check that. Okay? Only these two are things. So therefore, for 4 points, even if we just randomly put them like that, instead of putting them in a line, we already do not have shattering. Yeah, so it's harder to shatter. Okay? This is not shattering. This is just arbitrary 4 locations, right? You can imagine any kind of random 4 points will look like this, right? That you cannot shatter. So in fact, 14 is the maximum number you can get. Yeah, the maximum number of dichotomy vectors that you can get when you have 4 points. Yeah, 14 is highest. You can prove this actually, but of course we won't be able to do it here. Okay, 14 is maximum. You can never shatter, in fact. You can never get to 16 when you have 4 points, no matter what. Okay, so that's another thing to remember. So therefore, this kind of so-called quote-unquote effective number of hypotheses that we're looking for depends on L, depends on the data set that we have. Yeah, it is no longer just something that's like separate from the definition of the data points. So we're going to call this the growth function. If we ignore the impact of the locations. So basically, we look for the worst case of this size of the hypothesis. The worst case for the in terms of location that you can choose for the x1s, x2s. And we call it the growth function. So it's a function of h, also a function of the number of points we have. It is the maximum over the possible locations of the points of this size of the dichotomy set. Like that. Okay. So again, this is the worst case among all possible ways that you can be given endpoints. Right? So this way we get something that's independent of the location of the point that you're given, right? And in fact, now this one is what we're going to use as the effective number of hypotheses. Okay? We just want to remove the impact of, or remove the dependency on the data points. Yeah, everyone okay with this definition? Yeah. Yes?
So here we're only considering linear classifiers?
No. This is for in general. Linear classifier is only an example, right?
And then it exists within that bound.
So yeah.
It exists within the bound of 2 to the power of n.
Oh, 2 to the power n is, it doesn't matter what you have, right? There are only 2 to the nth power many binary vectors, right? Yeah, so this has nothing to do with anything else. Yeah. So let's look at a quick example of this growth function then. If we have a linear classifier, so this is our learning model, right? And with d equals to 2, okay? So basically in 2-dimensional space, right? Linear classification in 2-dimensional space. And we know what is the growth function of 3. What is this equal to? The worst case is 8, right? We already have an example, right? Yeah? We already seen the example with 8. So certainly, and 8 is the maximum already, right? 2 to the subpower is the maximum you can get. Yeah? Therefore, we know the worst case must be 8. Right? Yeah. But how about MH of 4? Well, just by the fact above, right? 14 is the highest possible that you can get for 4. Therefore, MH 4 equals to 14. Yeah? And we have an example to give you 14. Okay? So that's a clear example. A clear answer is 14. So now, given this effective number hypothesis, yes? Yeah. Worst case is all relative. Yeah, what do you mean by worst and best? Yeah, but it's just the extreme case. Yeah, extreme case. So we can use this effective number of hypotheses to replace the m that we have before in our bound, in our generalization bound. Okay, but because of this, it's not quite exactly the real number of hypotheses, right? So the numbers will change a bit, but we have the same form for the bound, as you will see. Yeah, so we have a new bound for generalization error based on this effective number. So it's a fact, has been proven that the probability, again, we care about the generalization error. So G is the final hypothesis after training with the training data set of n points. We want to find this, right? Turns out to be now upper bounded by 4 times mh times 2n e minus 2, not 2, 1 over 8. N epsilon square. Okay. Now let's compare that one. Recall the union bound that give us what? Give us less than or equal to 2m e minus 2 times n epsilon squared, right? Yeah, that's what we have. Similar form, right? You just replace this m by effective number of hypotheses, except the small trick is that you cannot use m points, you have to use 2 m points, just a technicality in the proof. Okay? And then the rest is pretty much the same, yeah, but then you have to change the minus 2 to 1 over 8, just to make the math work. Okay? The proof is in the textbook if you want to read it, but I would say, yeah, there's no need if you don't want to bother with this kind of algebraic details. But the whole point is that now we have successfully replaced the number of hypotheses by the effective number. Yeah. Where the number of hypotheses can be infinity, but the effective number is finite, right? In the linear case, in the linear case, m is infinity. But our effective one is only a of 14. Well, it's going to be dependent on n. Yeah, it just go up as n. Yeah, so depends on what n is inside. So again, then we do the same thing. We can set the delta to be equal to that side. Yeah, for mh of 2m, and then e minus 1/8 epsilon square. Yeah. Then, of course, we're going to get epsilon is equal to this a divided by n log of 4 times the growth function. The growth function is just a fancy name of 2n here. Fancy name just for just an effective number hypothesis. Then we can have the theorem if we just look at one side of that bound for the E out. And now this is called the VC generalization bound. And this is kind of our main result. And VC is by the two names, Vapnik, and the C is a chevron. I have to check my notes to chevron Nancus. Yeah. Oops. Wow, where did it go? Sorry about that. Here we go. It's in late 1960s to 70s. Yeah. The reason is arranged because they wrote this in Russian. The original paper was in Russian, and took a few years for the information gets to the West, translate into English in the early 70s. This one says. For any delta that's greater than 0, of course, yeah, with probability, same form as what we have, yeah, probability, 1 minus delta, we have E out less than E in plus that thing, that's epsilon, right? A of A over n log of 4 mh. 2m over delta, like that. Okay? Yeah, everyone's okay so far? Yeah? So we have come up with a new bound that only uses this effective number hypothesis now. Yeah, very nice, right? And this one, as I said, it can be quite small, but we still want to care about, well, how fast can this grow with the n, right? If we have a big data, if this grows very fast, that's no good. Yeah, let's check, let's figure it out. Yeah, so how to, in general, how do we estimate this growth function? How to compute or bound this effective number of hypotheses? Yeah, and it's still part of the contribution of Vapnik and Chevron-Nancus. So first thing is to recognize that this guy has a natural upper bound is what? This is the maximum possible how many binary vectors you can generate, right? Clearly this is upper bounded by 2 to the nth power, yeah, as the set of the dichotomy set size is also bounded by this, right? If we use this one, 2 to the nth power, plug into the generalization bound, would that help at all? Would it be good? Why not? What's wrong with it? Take the log, right? Take the log, you get n out, and n cancel out, right? Does not tell you anything about what happens when n is large, yeah? Right? That doesn't help, so we have to do better than this. We have to come up with a bound for the growth function that is better than exponential. And one major contribution of VC is that they provide this bound, which is a polynomial in M, based on what's called the VC dimension of your learning model. Okay, so let's get there. Second thing to note, yeah, to get to a better bound than this, is let's suppose we look at the case of 3 data points. Yeah, let's first look at an example. What we have before: x1, hx2, hx3, and plus plus plus, plus plus minus, plus minus plus, minus minus like that, and then you have the minus, yeah, on the other side like that. Suppose there is some x1, x2, x3 for you to get to this all of 8 possibilities. Okay, so if mh3 equals to 2 to the third power, yeah. In other words, there exists x1, well, let's say x1, x2, and x3, such that, right, because mh is the worst case, right? So you must have one case for this to happen, yeah, for one case of the location x1, x2, x3, such that the H has enough, yeah, H can generate all 8 cases. Right? Suppose that's the case. So all of them are okay. I claim then that for mh of 2, it is also going to be equal to 2 to the second power. Okay? Why is that? If I, for example, if I just look at these 2 points, right? Yeah. If I can generate all 8, then I can certainly generate those 4 with those 2. Yeah? Okay, so, yeah, then certainly H must be able to generate all 4 cases for any 2 of them, 2 of those points. Yeah. So therefore, I know that this tells me that mh of 2 is equal to 2 to the second power. Yeah. So whenever you can basically shatter at n level, you can also shatter at n minus 1 level. Yeah? It's very clear, right? Just because it's just a subblock. So in fact, I can generate this from 2 to 3 to any general k, right? So in fact, more general, if mh of k is equal to 2k, yeah, you can generate all of them for some k. Then I have mh of n equals to 2 to the nth power for all n that's less than k. Right? Yeah? You just go back step by step. It's all of them can be generated. Yeah? Is that right? Just from the previous example, right? I can generate, if I can have for the 3 points, then there are 2 points there, I can generate all of them, and so on. There's 1 point and so on. Yeah? Okay. Is this convincing to everyone? No? But how about the previous case? If I have 3, then I can generate 2. I have that, right? So therefore, you can easily say I have 1, I can also generate. Yeah? Or what if you can say I have 4 points? I can generate all 16 of them. Then for a subset of 3 points, I can generate all 8. Right? So if you have 4 to be shattering, then I have 3 shattering. 2 is also shattering. Just by induction, step by step, going backwards. Yeah? Because they are just subsets, right? You can just look at the subset of points. Yeah? There exist those points for you to do shattering. So in general, we're going to have a figure that looks like this. If I look at the axis that has n, yeah, starting from 1 point, 2 points, and so on, 3, 4, 5, I don't know, yeah, whatever, right? I can always separate this axis into two parts. See, at this point, and backwards, all the way to 1, this is as diverse as possible. Yeah? But then start from this point, I'm strictly less than 2 to the nth power. Right? Because once I have one point where I get 2 to the nth power, all of the other points will have the same property, right? Yeah. So they will be consecutive block. Entire block, we have full shattering, and then we have a block that you cannot. Yeah? Right? Is everyone convinced about this point? Yeah. Basically, there's no holes in the middle. Right? We cannot have a hole here that says, oh, for this n value, I cannot get to 2 to the nth power. Yeah? If you can get one here, then all of them below, you have 2 to the nth power. Okay? So that's basically this example. This example shows you. This is, in general, we have this conclusion. Yeah. So there is a boundary somewhere. Yeah. Boundary between 2 to the nth power and less than 2 to the nth power for the growth function. Yeah. And the boundary point here is called the VC dimension. So that's the definition. The VC dimension of a H, the hypothesis set, denoted by usually dVC of H, like that. Is the largest M such that the effective number is 2 to the nth power. Yeah. Now remember we say that, well, 2 to the nth power is the upper bound to MH, right? Upper bound to MH, and we don't like that. If you put this 2 to the n power there into this bound is meaningless. Yeah? So VC dimension gives you the largest n that it has this property. But once you get bigger, when you have more data points, turns out that this effective number hypothesis is going to grow less than 2 to the nth power. Yeah? So that's good, right? That's what we want. Yeah? We want this growth function not to grow too fast. Yeah? So it turns out if you go beyond the VC dimension, then it does not grow as fast. So for example, for the linear classifier, let's see what happens. Linear classifier. Again, we assume d equals to 2. Yeah? Then we know that MH of 1 has to be equal to 2. MH2 is equals to 4. MH of 3, we also know equal to 8, right? And then MH of 4 equals to 14. Yeah? So 3 is the largest one, right? Where you still can get 2 to the nth power. So therefore we know that dVC of this linear classifier equals to 3. Yeah, for linear classification in 2-dimensional space. Okay. Now how do we use the VC dimension? Well, again, these two guys, they prove a very nice theorem to bound this effective number hypothesis that says, well, there's an intermediate step that we don't need to care a lot. I guess this one you can pretty much ignore. Says the dVC of H, and then it's M choose I. And then this is upper bounded. The final one is important. dVC of H plus 1, like that. Okay. Again, the middle one you can ignore. The proof is in the textbook if you want to look at it. Pretty tedious. Yeah. But the final result is important. Why is this better? Remember previously the alternative is 2 to the nth power, right? Now this one is polynomial in N. Yeah? DVC, for example, in two-dimensional space for linear is only 3, right? So this one with cubic in N for linear classifier in two-dimensional space. Yeah? So this is polynomial in N, yeah? Instead of 2 to the nth power. Okay? So if you have a way to calculate the VC dimension for your learning model, then you have a very tight bound for your generalization. Yeah? In fact, here in two-dimensional space, the VC dimension is 3. Turns out that if you do linear classification in d-dimensional space, then the VC dimension is d plus 1. Okay? So you still have this nice kind of a polynomial. So therefore, if we go back to the previous example, so linear classification d equal to 2, right? In that case, then our E out of G will be less than or equal to E in of G plus, what is that? Just substitute that in here, right? Log of 4 times, supposed to be Gauss function, but now we have E cubed, N cubed. Again, this is equal to 2, right? Over delta. Yeah? Right? Just substituting this bound into that. That's the other side. Yeah? So what does this tell you now? What if we have big data? We have a lot of N. What does this approach is? This is log of N cubed. So it's essentially just log of N, right? The cube can take out, it's a constant times log, 3 times log of N. So log N over N as N goes to infinity goes to 0, right? So that's great. So now you know for linear classification over two-dimensional space, you have 0 generalization error if you have enough data points. Yeah. And in fact, for any D, yeah, if you know that you can, in fact, you can see there's a proof in the textbook that the VC dimension for D-dimensional space, linear classification is D plus 1. So all of this still hold. So learning is possible. In fact, learning will work very well, yeah, because of this. Yes. Okay. Yeah. All right. So I know. So today is pretty heavy, right? That mathematically a bit. So next time we're going to just wrap this up by looking at a few examples of the DV for different learning models, and then we'll go to the case of regression as well. How can we argue about whether you can learn well or not for regression rather than classification? Okay. We'll continue next time. Then. Yeah. So see you next week.
I had to submit a homework request.
Okay.